Assalamu alaikum, students. So today we start with how the kidney regulates osmolarity. And as mentioned before, the way to deal with osmolarity, the kidney basically manipulates water. So this lecture is part of a two-lecture series where first we will introduce what we mean by water balance. Um, and these are the learning objectives. Today we'll review some of the stuff that we did in the first lectures when we started this renal unit, where we talked about ECF osmolarity and volume. This is stuff that you should be now very familiar with. Then we'll move on to CNS centers, which are involved in osmoregulation. We'll look at these two, mainly osmoreceptors and thirst center. Then we'll review ADH, antidiuretic hormone, in detail. Where does it come from? What does it do? And what are the consequences? Which are the conditions in which ADH, without ADH, you won't be able to deal with those situations. It's crucial. And at the end, we will go through some overviews of how kidney deals with uh, uh, overhydration, where there is abundance of water, and dehydration, when there is water scarcity. Details of which, specifically renal response to dehydration, we'll be talking about tomorrow, which is that famous uh, issue or question of how does the kidney concentrate urine. All of that action will be tomorrow, but this crucial lecture basically introduces the whole thing and gives you some very important details about how where the CNS is in terms of osmoregulation, what does ADH do, and the very important overviews of this whole osmoregulatory scenarios. Right. So this is that stuff which we have discussed. Please remember that whenever we talk about ECF volume, we are looking at primarily, not exclusively, primarily sodium. So it's sodium homeostasis. That is how kidney basically regulates ECF volume in the body, and by manipulating water, controlling water homeostasis, it deals with changes in ECF osmolarity. This is that stuff that you should know. This is a nice diagram that I found. On this side, you have volume and three scenarios: increase, no change, decrease, and then you have osmolarity. Again, you have three columns: decrease, no change, and increase. In the center, you have normal, volume, and osmolarity. So this is where there is no volume change and there is no osmolarity change. You can, on your own time, in your own time, you can review, discuss with your colleague how does each of these boxes, uh, what concept do they hold in terms of both osmolarity and volume. Remember, this is the stuff that we did in the body fluids lecture right at the beginning, and I will try to put a link here on this slide so that you can always go back and review that. Okay. So now we are basically coming. Our focus is now on water primarily through most of this lecture, and here we see that in women, again the standard is to take the 60 kg woman and the 70 kg man. This is tradition, convention rather in medicine. So a 60 kg woman holds about 30 liters of body water, and a 70 kg man about 42 liters, and roughly most of this water is inside the cells, about 3 liters in plasma. Remaining 11 is interstitium. Again, this is information that you should already know from those first lectures. This I found it's a good diagram to tell you how the homeostasis is achieved. If you look at this, input and output is basically is supposed to be zero. So whatever water you take in and whatever you give out, it should be in balance so that there is no net gain of water, because net gain of water, as the theme of this lecture now, will sort of affect your osmolarity. Okay, so you should not have a net gain or loss of water, because that has now, that you should now be clear that that has direct relationship with osmolarity. Okay, try to build that concept in the mind. Secondly, what you need to understand is that uh, the body can the kidneys cannot invent water, quote unquote. Okay, they can only conserve water. The introduction of water is mainly by gaining water. You drink water, okay, and basically it's in the food and drink. Some of it, very few of it, is the result of metabolism. So this is the average amount of. Of course, the temperature varies, but you're talking about a moderate temperature, atmospheric temperature. You basically gain 2.5 liters a day on an average, and the same is lost by insensible loss through sweating, etc., through lungs. Urine is the main output of water every day. Then you lose some in feces as well. The bottom line is both, they both need to be balanced out so that osmolarity is constant. Okay, so now we're talking about the entire system of water homeostasis. Uh, Remember that ADH, osmoreceptors and ADH, this is where the kidney will be discussed extensively. Thirst center is a CNS center which is basically to do with drinking behavior. So this does not have directly anything to do with the kidney. However, this is where the kidneys mentioned would be extensive. Okay, that's one thing. Second thing is that osmoreceptor ADH and i.e. kidney, this all of this is geared towards reabsorption of water or letting go of water. So if you are overhydrated, the kidney will let go of extra water and the osmolarity will be maintained. Conversely, if water is deprived in the atmosphere, if you're water deprived, then kidney will conserve extra water, which would have rolled out under normal circumstances. The kidney will, in this case, uh, conserve that water, and hence osmolarity again will be maintained. So the main point of this system, this whole system, is water management. Okay, of already present water or the lack of it in the body. It does not have much to do with drinking or water intake. That's mainly the role of the thirst center. Okay, the thirst center basically regulates your drinking behavior. Okay, now this is drinking behavior can be psychogenic. Some people just drink water without the need of water. They probably surf the internet too much. They look up health articles which are not uh, totally scientifically based many times, and the generic message is that you should keep yourself well hydrated, and these health messages, so called, are not very detailed in the sense that when should you keep yourself more than usual hydrated, and what is the meaning of well hydrated anyway. Okay, so whenever you feel thirst, that's the signal of the body to take water in. If you're drinking water anyway, then that's that. You're going to lose that water. You're not going to benefit from it hugely. So we are not talking about that behavior where you just carry on a bottle and you just keep on drinking it. We are talking about the drinking that is required and that is generated by an actual center in the CNS, which responds to osmolarity. Okay. So the arrangement of the lecture is we will be discussing this first, and then this. We'll be ending on the third center. Okay, so this is an overview of where the CNS stands in this whole saga of osmolarity regulation. So what he has done is he has blown up this part, the hypothalamus part here, or rather this whole thing here. So this is the magnification. This is the pituitary, as you can recognize. Uh, this is the stalk of the pituitary, and the master planner, the hypothalamus, is nicely tucked away, looking over not just anatomically, but very much physiologically speaking. looking over the pituitary gland. And you can see all sorts of connections here. So let's just go in sequence. This area here, this is the osmoreceptors. So these are receptors which basically sense the blood osmolarity. Okay, so this should be very clear. Osmoreceptors are area is the area of the hypothalamus which senses the it's a receptor, so it obviously senses something. It senses blood osmolarity. Blood osmolarity goes up, blood osmolarity comes down. These are the receptors which pick the signal up, and once they pick the signal, they stimulate supraventricular nucleus, which is a famous nucleus of the hypothalamus. You have read this in hypothalamus when we're discussing the limbic system. And then there is a paraventricular nucleus. Again, it should be similar, so familiar now. We covered it when we were discussing limbic system. So these two nuclei come into play when we are talking about ADH. Okay, so osmoreceptors, when they get stimulated or when they get destimulated, they affect supraventricular and paraventricular nuclei, which share ADH secretion. More two-thirds of ADH secretion happens in supraoptic nuclear neurons, and paraventricular is responsible for one-third of the secretion of ADH. Now, both of these, remember, ADH is formed here. It is then transported by this tract and stored in the posterior pituitary, and then gets released here in the blood. Okay, so it's a neuroendocrine hormone. A few words of caution. ADH is not manufactured, not made in the posterior pituitary. It is made in the hypothalamus, stored in the posterior pituitary. Please make a note of that. Okay. Now, second, there are only few hormones which are called neuroendocrine hormones. ADH is one of them. The other is oxytocin. Oxytocin also is manufactured here in the hypothalamus and transported in a similar fashion and stored in the posterior pituitary till the signal comes and it's released. Okay, so these two hormones are famous and distinct in the sense that they are called neuroendocrine hormones. Now, what do we mean by that? What we mean is that, look, they are formed by neurons and yet they're hormones. It's an off-throwing line, isn't it? What are classically, how are hormones defined? Hormones are substances, okay, which have specific functions, which are released by glands, right? Endocrine glands directly into blood. And then they are carried away and they do their business. This is a classical definition of hormones, okay? But here, you don't see a gland. You see neurons. And now, what are neurons? What do neurons make? And what is that called? Neurotransmitters, right? The neurons make neurotransmitters. Sympathetic neurons make norepinephrine. Norepinephrine is a neurotransmitter. However, here there's a special case now. These are those exceptions which need to be remembered. Here, neurons are making a substance which is carried away by blood. Now, if somebody makes something and is carried away by blood, that qualifies it to be a hormone by definition. However, now this thing that has produced it is not a gland, but it's a neuron. So we make another category for this. We say that it's a neuroendocrine system or neuroendocrine hormone produced by neurons, taken away by blood. So it's like it takes something from both worlds, neural world and hormonal world. Okay, so that's that. Please do keep in mind these connections. These are very important connections. Interestingly, this whole system has a link from the vasomotor center, which you remember from circulation, the baroreceptor reflex, which brings in pressure-related information from the blood vessels to the vasomotor center. This has an input on both nuclei, as you can see clearly from here, and we'll be talking about this in a bit. Okay, so these nuclei, finally, these nuclei are under two influences. One is the plasma osmolarity, which is mediated through osmoreceptors. And then there is plasma volume, ACF volume, sorry, ECF volume, not plasma specifically. It's the entire CVS as ECF. So ECF volume information is being communicated from the VMC, while the ECF osmolarity is being conveyed via osmoreceptors. And then you have the ADH secretion from these nuclei, which is adjusted according to these two stimuli. Please remember that mostly this whole system is set, is triggered or inhibited. Mainly, the main stimulus is osmolarity, ECF osmolarity, and less so is blood volume. In said in another way, it is uh, very less sensitive to changes in blood volume as compared to or when compared with changes in osmolarity. It's more sensitive to osmolarity, ECM osmolarity. Okay, so we've talked about ADH. ADH, another name is vasopressin or arginine vasopressin, AVP. You may find in some books ADH is written as AVP. Arginine is again a typical composition of this hormone biochemically. Vasopressin is a good term in the sense that it gives you a flavor of the of this hormone, and ADH is basically it's functional. The abbreviation also, it also has its function in it. Anti-diuretic hormone. So if diuresis is the act of uh, releasing urine or getting water out through the urine, anti-diuretic means that something, this hormone basically inhibits that, inhibits the outflow of water or limits it, and promotes the, very importantly, reabsorption of water. Okay, so ADH is to do with reabsorption of water. Okay, as we'll see. Now, this is a rather busy looking slide, but this is just about everything that you need to know about ADH. And hence I put all of this in one slide. Okay. Right. So we start with the anatomy first. Okay. Let me just readjust this. Right. This. This now is we have come to a schematic diagram. You can see the hypothalamus, you can see the tract, then you can see the posterior pituitary, AVPC. It says AVP here, arginine vasopressin. This is basically ADH, made and packaged in neurons of the supraventricular and paraventricular, supraoptic and paraventricular nuclei. These vesicles then are transported and then are stored here, where they can be picked, released in the blood. This is something that we've just done. Okay. Now, coming to what shall we do first? Let's tick this off. Plasma osmolarity. We know that this is the normal range, 280 to 300, and see how sensitive vasopressin ADH release is. As you increase plasma osmolarity, ADH secretion goes up. So that's that. We've done that. Coming to this now. This is a nice, extensive, not extensive, but nice schematic flowchart. And look at the key first. The yellow sort of this shape is the stimulus. This rectangle, its color code may not be appreciated over probably over YouTube, but let me tell you that this stuff, right? This here, these three boxes, they are the sensors. Okay, then these boxes are the input signal. This is the integration center. This is the output, and this is the target tissue response, and then systemic response. It will all make sense when we do do this, solve this. So we said that ADH basically is released in relation with osmolarity. This is a nice line, one line to remember. High osmolarity or low blood pressure causes ADH secretion. It's a nice line. High osmolarity or low blood volume or both. Okay. Now, before we do this, let's do the osmolarity thing because it's most sensitive to osmolarity. Okay, anything greater than 280 milliosmol per liter, ADH should release normally. Okay, where is where is the sensor of this? It's hypothalamic osmoreceptors, as we just discussed. Which is the input signal? interneurons of the hypothalamus. All of this is happening in the hypothalamus. The neurons in the hypothalamus, we've talked about the two sets of neurons. What is released in relation to this stimulus? ADH is released. Its secretion is enhanced, increased. Okay, what does it do? What is the target output signal is collecting duct epithelium. What happens over there when ADH goes there? It inserts water channels, or they're called aquaporins. Okay, uh, aquaporins or water channels are inserted. We'll talk about that in a bit. And when they're inserted, you have now the power to increase your water reabsorption, to conserve it in a situation of dehydration. Remember, the osmolarity was increased. So you have a situation where you have less water to solute ratio. Okay. So you need to conserve water to bring this osmolarity back to normal. Okay. Now, this would not have been possible if ADH wouldn't have been there to use its power or magic so that you can squeeze out the extra water from urine, which you wouldn't have done if the osmolarity was okay. Okay. So, in other words, when osmolarity increases, you take out from the urine more water than you would usually do. How is that possible? Well, there are two reasons. I'll give you one right now. ADH related aquaporin insertion in the collecting duct enables you to pick up more water than your usual scheme of things. Okay. The other, I will let you know as we flow along. Okay. Right. So we've solved this flow chart on osmolarity. Now let's quickly see what's happening here. Decreased blood pressure, uh, or any due to any volume loss or whatever. You see that what who brings the signal, who gets disturbed by this? The receptor is carotid and aortic baroreceptors. Remember, we mentioned baroreceptors in the initial diagram as well. The sensory neuron of the hypothalamus picks this up. Hypothalamus then starts making ADH. Remember, this is new information for you. What you read is the baroreceptors take information to the VMC in the brainstem, and you have all sorts of sympathetic or anti-sympathetic responses, which brings the blood pressure down or up, whatever is required. Now you are studying that that's not the only thing decreased blood pressure do. So this is important and crucial information for you, which you need to add to your blood pressure scenario. Okay. So when you decrease blood pressure, not just is the VMC become the boss. You also have that signal sent to hypothalamus, which then starts to, if there is a decreased blood pressure scenario, then the hypothalamus will start to make vasopressin, and then vasopressin will do its whole thing, similarly to what it did with decrease in osmolarity, increase in osmolarity. In this decrease scenario, ADH will be released. It will conserve water, and that water will go to ECF volume, make up for it, increase the blood pressure. Simple. Okay. Now, uh, decrease atrial stretch due to, so there are atria, this is the heart. Atria have stretch receptors inbuilt in their walls. If there is decreased volume of blood, these stretch receptors pick up that signal and then send it off to hypothalamus. Hypothalamus makes ADH. The same thing happens. Water is conserved, ECF volume is accommodated, enhanced, and hence those that stretch or lack of stretch signal by the atrial receptor is snubbed, or it's worked against. So these are the main things. The main being osmolarity and blood pressure responses on the release of vasopressin or ADH. Right. So we've been talking a lot about kidney, and this is obviously a kidney class. So we will now see, and I thought I will discuss it right here, so that when in Guyton does it a bit differently, but I think you should know this as part of your info diagram on ADH. So you know all you need to know about ADH. So whenever any book mentions ADH does this, does that, you know what ADH the holistic picture of ADH is. That's why I put everything here. So next time I will just mention that ADH increases. I will expect you to I will expect you to respond or understand when we say that ADH increases. This happens in the kidney. Okay. So today and mainly tomorrow, we'll be talking a lot about ADH increases in scenarios where ADH is increased. Please remember that when you think about the kidney and ADH, this is the diagram which becomes operational. Okay. Now check this out. ADH came from the blood, obviously. Okay. These small boxes is ADH. This is where we start. So the ADH came in, it got transported into the interstitium, where it found the collecting duct cell with its receptor. It connects with the receptor. Please do read up on which are the receptor types and this, that, the other. That is a tutorial material, and you need to read up on this yourself as well. So vasopressin binds to its membrane receptor. There is a intracellular change which is mediated by cyclic AMP, and that basically activates the receptor and the second messenger system, which you will read detail about in endocrinology. But let me just say that second messenger systems are intracellular messenger systems, which are linked with their typical receptors. When you activate the receptor, you basically not just activate one thing in the cell by by allowing the key of this receptor to come and connect with it, which in this case is vasopressin. You are activating a whole cascade of intracellular reactions called the second messenger system. Okay. So in this case, that second messenger system is being played out by the cyclic AMP, whose level it increases when you activate the ADH receptor with ADH. Now, there are the storage vesicles, which are which have aquaporin stored in them. They are activated because of this signal. They are already, remember, they are already pre-made as well. Not just these, this also activates the formation of aquaporins. Aquaporins are proteins, right? So who will make them? Who makes proteins in the cell? The transcription process. So specific genes, aquaporin genes are activated, which are transcribed, then translated, and their formation also increases. But that takes time. So that's why we have pre-made stuff already available for immediate release. And then that genetic machinery also gets started to make more and new aquaporins, so that if you need it, in the current scenario, it becomes available in a few hours, but you will need it anyway. So the things that have been used up are replenished by the newly formed aquaporin vesicles. Right. So these aquaporin vesicles, when they are activated by the secondary messenger system, they go and they basically fuse with the with the apical side, the lumen side of the collecting duct. When they fuse with the membrane, what they contain, the aquaporin itself, it gets plugged into the membrane, the apical membrane, like this. So this is the vesicle. It got activated. It contains aquaporin. It became when it became activated, it fused. When it fused, it basically forced its content and pegged it inside in the membrane. So now you have a channel of water which you induced, which you have created just now, which wasn't there before. So this is an additional water channel now in this membrane, through which extra water can be transported and reabsorbed. Okay, so this is that overview of what ADH does and how does it increase water reabsorption. This is how it increases water reabsorption. Again, a word to note, important point is, since it's all of this business is hormone related, hence it's reversible. Okay, water reabsorption via, say, paracellular pathways through the tight junctions is constant. You can't do much about that. It's a constant feature. Uh, it's like you have a window in your wall. That's a hole, right? That's a hole in the wall. It's constant. If you drill a hole in the wall and then use plaster of Paris to plug it, then dislodge the plug, then plug it, then dislodge the plug. Let's say that is a reversible hole in the wall, but the whole window is irreversible. Let's assume that it's irreversible. So there are pathways for water transport which are fixed. You can't do anything about that. However, this ADH mediated aquaporin system is reversible. So you've understood what happens when ADH comes in. Now, if you think about if ADH now decreases in the blood. Now that you have reabsorbed water, obviously it's a negative feedback mechanism. So when you have water reabsorbed in the blood eventually, and that increase osmolarity scenario is now addressed, osmolarity goes back to normal. The vasopressin will obviously drop in the blood. Yes, this whole reaction will drop. Yes, aquaporins will stop being inserted into the membrane, their levels will drop, and hence this newly created temporary extra water reabsorption scheme that you concocted, this also vanishes. Okay, so this is a reversible water reabsorption business, which comes only into play when you need it by meddling with osmolarity, increasing vasopressin, and this, that, the other. Okay, remember this. The rest of the water reabsorption is constant. You need to have an obligatory urine volume for which you need to have a constant level of water in the urine. The fluctuation in that water is being discussed here. Okay, right. And then you can imagine, like, look, if we have solved this scenario for increased osmolarity, you can very easily solve it for decreased osmolarity. And I will leave it up to your imagination that if I were to say osmolarity lesser than 280, then you should now be able to solve this using this diagram. Okay. So the only thing left is this nice table that details increase ADH. When does it happen? In this scenario. Decrease ADH. When does it happen? It happens in this scenario. You just need to remember this. Remember, nausea and hypoxia are interesting entries for increase ADH. We have done these top three, which are the mainstay of the most uh, prominent of ADH handlers. However, nausea comes in important in the top five, and so does hypoxia. And then the reason I selected that, it also mentions some drugs that affect the ADH. This will come in later on when you go into your clinical training, inshallah. So this is just about all that you need to know on ADH. Again, it's not exhaustive. Not no claims are being made that everything that you need to know, but what you need, at least at this level, is on this slide, inshallah. You can always look up certain advanced texts to read up a bit more on vasopressin. It is a very important hormone to remember, not just from kidney point of view, but from cardiovascular point of view, from the working of the brain, the hypothalamus point of view. So a lot of worlds come in, get united over here. Okay. So now we've dealt with the CNS side, which deals with osmolarity from the ADH point of view, the ADH axis. Okay. Now we turn our attention to a minor, not less important, but lesser mechanism. I shouldn't say it. Functionally, it's the same. The point I'm trying to make here is that the machinery dealing with osmolarity and ADH is bigger, it's more prominent, it has more afferents, etc. And then you have another mechanism uh, which physical representation wise is slightly lesser. However, its physiological importance is still very, very important. So these are the two areas which are postulated to be thirst centers. Similar areas which release ADH also are postulated to pick up thirst. So when you become thirsty, actually these areas are the ones which make you feel that feeling of thirst. Okay, and of course they respond to all those major mechanisms which get ADH release. So this is a simpler topic. Just remember the ADH triggers, they also happen to be the triggers for thirst. However, in this you have an entry. The last two entries are important and interesting as well. Angiotensin 2 also triggers thirst. Mind you, angiotensin 2 also triggers ADH. Okay, angiotensin 2 does a lot of things, and if somebody could remind me later on WhatsApp, I can put up a consolidated diagram for angiotensin 2 as well. Maybe the CR can make a note of this, please, and remind me through WhatsApp later. We can have a nice one, similar to what we did with ADH. We can have a big one slide info slide regarding angiotensin 2. Okay, this last thing is very important. Dry mouth is a trigger for thirst, and gastric distension is a an inhibitor of thirst. Now, uh, you must have felt a dry mouth sometimes in your life, and this is where we fast, or you're traveling, or the weather is extremely hot. Lahore being one of the cities which can get very hot in the summers. Dry mouth is not just a thing that you have. In physiological terms, dry mouth is actually a stimulus for thirst centers. It stimulates the afferent information going from a drier mouth goes to the thirst center directly. It's one of its most prolific stimulators, and it stimulates the thirst center so that you feel the urge to drink water, which immediately wets the mouth, and hence this afferent information is snubbed. It decreases. This is something to note. A dry mouth is actually afferent information, stimulatory information for thirst center. Also, if you think about it, when you drink water, the mouth and the upper parts of the GIT become wet, right? So check this out. You have a osmolarity issue in the body fluids. Okay, the osmolarity has gone up even more than 300. Okay, now when you drink water, obviously you will feel the urge to drink water, along with all that ADH business which would have started automatically, but that is subconscious, right? What is conscious is the feeling, the only conscious feeling that you get in an increased osmolarity scenario is thirst. So what you do, you drink water. Now this water goes through the mouth, then the upper esophagus, and then down, and then the stomach, and then so on and so forth. But there's a problem. The problem is the absorption of water is in this intestine. And there's a time lag between you drinking water and its eventual absorption, and hence it's coming into blood, addressing that osmolarity issue, bringing the osmolarity back to normal, etc., right? But I want you to slow this down and think about the time lag that it takes from drinking water and its absorption. This is where the ingenious design of the creator in all of us comes to play, and it's evident. When you drink water and when you absorb water, there is a time difference between. So by the time the osmolarity actually in the blood gets addressed, if you don't stop drinking water, you will swing in the other direction, wouldn't you? You would over intake water and make your blood dilute. Shouldn't there be a mechanism which stops the drinking urge so that you take just enough water, and when you take just enough water which is appropriate to address the osmolarity issue, somebody needs to tell you that okay, now you should stop water intake. In English we call it the thirst has been quenched. The thirst has gone. The urge has stopped, right? When you drink water, think about this. When you drink water and when you had your fill, as we say, the third quenches. However, the osmolarity problem is still there. But just because of this time delay thing, to protect you from diluting your blood, the thirst center, by detecting the wetness of the mouth and the upper GIT, it turns off the thirst mechanism just in time. So it's a protective mechanism so that you don't ingest too much water. When the wetness is achieved of the mouth, the thirst center inhibits the thirst or decreases it as you are moving fluids through. And then when it calculates that, okay, this is quite enough. So you can imagine the thirst center being so intelligent that it actually predicts that, okay, this amount of wetness, I mean, we don't exactly understand how it works, but we can postulate that it has it calculates from the afferent information, which is the wetness of these surfaces uh, at runtime, mind you, live. Uh, right now, you not necessarily have adjusted the osmolarity of the blood because that will take time. So it's just really mainly the wetness and the distension of the stomach by which it can calculate that, okay, enough water has gone in. Let's switch this thirst thing off so that the dude stops drinking water, so that he doesn't end up diluting his blood. Okay, something to think about. It's actually a very cool phenomenon. It's when I first read it, when I was your stage, I was quite fascinated. Okay, just an important note before we go into the last part of this lecture. Plasma osmolarity, we've been talking about that. It's not routinely checked, by the way. So seldom would you write as a doctor a plasma osmolarity to your lab. What you will do is do the shorthand is, by the way, this is a longer test and it comes back in routine. It's not given because it has a time lag issue probably. The easiest thing to do is go for your sodium concentration, which is routinely checked anyway in your electrolytes. Sodium is can be very easily checked, and deduce you can deduce the plasma osmolarity because it's one of the 94% of the ions is basically sodium sodium, and the rest of the ions are represented by this factor of 2.1. You multiply your sodium concentration with 2.1, the result is a pretty decent picture of plasma osmolarity. Again, if your patient is critical, then you want to go for plasma osmolarity, the test. But in routine purposes, we just extract or what do you say? Extrapolate it from the sodium concentration using this formula, just as a footnote. Okay, so we will end this lecture by doing an exercise, the detail of which we'll be doing tomorrow. Okay, before we do that, I would like to remind you something that I mentioned at the start of the tubular function. I mentioned something regarding water, movement of water. If you recall, I told you there are no active mechanisms of water movement. Water basically moves down uh, its concentration gradient or in relation with solutes, okay, osmosis. So water will either go, will primarily, if you are only talking about water, we're not talking about solute, only water, there is absolutely no other way, no active transport of water. Water will always follow that simple diffusion process. This can be a problem, which I will introduce today and we will properly discuss tomorrow, okay, in concentration of urine scenario. And second is its manipulation through osmosis. You understand both of these, simple diffusion and osmosis. You know now very well. Now, let's say this is the issue. You need to pause the slide now and observe what's happening here. Here, in this, I have not given you the key. The key is in the next slide. This is something for you to try to crack it yourself. Okay, this is a a flow chart which is basically of decreased plasma osmolarity. So you had too much water to drink. This is overhydration scenario. Okay, this is dehydration scenario. Okay, if you could just pause and solve it. By solving, I mean just supply increase or decrease arrows for this section of the flowchart. and this section of the flowchart. Okay, you may pause it, solve it, and then move on. Okay, now moving on, this is the key. So if you just see, you should be able to do it very easily. If there is water abundance, the plasma osmolarity drops. It goes below 280. This should inhibit everything because everything is basically switched or targeted for increase in plasma osmolarity. So when you decrease plasma osmolarity, the osmoreceptors get inhibited, ADH secretion goes down. When that goes down, everything that ADH does goes down, and concurrently, when you have decreased plasma osmolarity, the thirst center gets inhibited. The drinking gets, you don't feel the urge to drink, and then all these things, they come together and increase plasma osmolarity. A, by decreasing input of more water, new water, and two, very importantly, letting go of water, increasing urine volume and getting rid of that extra water will bring down the osmolarity, bring up the osmolarity back to its normal situation. In this scenario, the opposite will happen. Plasma osmolarity has gone up. It stimulates the osmoreceptors. It stimulates the whole ADH and what it does scenario. It also stimulates the thirst center. The drinking is on now. You take more water in. You conserve more water and bring back the osmolarity back to normal by diluting the blood, the ECF. Now, the perceptive student will immediately see an issue here. Go on, think about it. Think about what the problem is. And this is related with water being a passive actor. You cannot actively pump water. There are no donkey pumps in the kidney, electronic driven donkey pumps. Okay, you have to do it the old fashioned way. So my question to you is, would you have a problem here getting rid of extra water? Or would you have a problem here where you have to decrease urine volume by reabsorbing more than usual water? Is this a problem? And if yes, why? Or is it this a problem? And if yes, why is that? So let me not answer that question. Let me see what you guys do in the comment section, and we will start proceedings from this point onwards in the lecture tomorrow, inshallah. I look forward to your educated guesses or maybe a bit of your analysis, inshallah. Okay. See you then till tomorrow. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.